So it's time to start the afternoon session. So we'll be having 5 speakers this afternoon, 3 before the break, and then 2 after the break. So our first speaker this afternoon is Terry Tao from UCLA. And around 10 years ago, Terry Tao, together with Ben Green at Oxford, they proved this tremendous theorem that there are arbitrarily long arithmetic progressions in primes. And that was a kind of classical collaboration with 2 people. And in more recent times, it's become possible to have collaborations among many, many more people at once, thanks to communication on the internet. And so Terry is going to tell us about Polymath Project's massively collaborative online mathematics.
Thanks, Brian. It's great to be here, and it's, of course, it's been a really quite unique experience, actually, this whole event. So this talk is not really about mathematics per se, but it's about the practice of mathematics, and a relatively new way to do mathematics, which I don't think will supersede traditional mathematics, at least not for many, many years. But it is one new alternative way of doing mathematics, which will be useful for certain types of projects. And these are these polymath projects. So these are projects which are massively collaborative, and in the sciences, we now have master collaboration is now very common. So, for example, in physics, we have these massive collaborations, like the discovery of the Higgs boson. Is the key paper has 3,000 authors attached to it, the Atlas collaboration, and this was recognized incidentally by the Fundamental Physics Prize 2 years back. Or in the life sciences, we have, for example, the Human Genome Project, which has a mere 237 authors, but many of those authors are institutes, which themselves have hundreds of people behind them. So certainly in the sciences, we have really big collaborative projects now. But not so much in mathematics. So in mathematics, it's always traditionally been 1 or 2 author research people working in isolation, and if you compare just crude statistics like number of co-authors in a mathematical paper, so I think it's been the average number of authors in a paper in mathematics has slowly increased from like 1.1 in 1940, almost nobody collaborated in 1940, to about 1.6 in 1990, and a little bit higher than that now. I think in the life sciences the average is now 4 or 5. I don't have the physics numbers available. And the percentage of single author papers has also gone down from 90% to like 50% today. So I mean, it's slowly getting more collaborative, but nowhere near as much as the sciences. Okay, so many of the great achievements in mathematics even today are still basically mostly 1 or 2 people working pretty much in isolation until they're close to completion, and then they announce the result after it's all done. So famous examples include, of course, Andrew Wiles, who worked for 7 years on Fermat's last theorem, pretty much in isolation. I think he told maybe 1 or 2 people what he was doing, until he finally had announced his proof in '93. Although he did collaborate later with Richard Taylor to repair a gap in the first version of the proof. And then a bit more recently, Grisha Perelman, of course, proved the point-Gray conjecture and the geometrization conjecture. Also worked alone for many years before announcing the result and then sharing it with everybody. And then last year, and closer to my own area, Yitang Zhang also worked for about 3 years on his own. Actually in rather difficult economic circumstances, actually, before he had his breakthrough result on bounded gaps between primes. So there are certainly, it's certainly still the case that many of the big achievements in mathematics are basically 1 or 2 mathematicians. But then there are other types of mathematical contributions which are maybe not so much solving a single massive problem, but for which we certainly do work collaboratively. I mean, famous examples include Nicolas Bourbaki. They did many things, but one of the things that Bourbaki did was they introduced this very influential set of textbooks, laying down the foundations of mathematics properly. I mean, in some cases, some of these textbooks have become superseded with more modern treatments, but still, some of these books, which were written, by dozens of mathematicians collaborating under the pseudonym Bourbaki, still very influential. And another famous example is the classification of finite simple groups, what's known as the enormous theorem. That we now have this list of, I think, all finite simple groups are one of 19 families. Well, no, like 5 infinite families, and then like 19 sporadic groups or something. And it's a massive, massive theorem. There's no single place where you can find the proof. It's tens of thousands of pages, over several hundred articles. There is over like 50 years to prove the whole thing. There's now a project underway to simplify the classification, but still the classification will still be, I think, about 1,000 pages long. Okay, so there are some really collaborative efforts, but not nearly as much as in the sciences. I think one of the reasons for this is that in the sciences, often the bottleneck is not so much the theory, not knowing how to do something. Often we know how to do it, it's just we don't have the resources. We need a super collider, or we need this huge investment to sequence genes or something. And so often the theory may have been developed for decades, but it's only at some point where the technology advances to the point where you can actually do something, and there you really need massive resources, massive amounts of money, manpower, or physical equipment. But in math, it's very rarely like that. In math, if we know how to do something in theory, we can probably just do it. It's not so much money or manpower which is the problem. So a typical example is the Riemann hypothesis. It's not a matter of, if we had an institute which had $1 billion budget to solve the Riemann hypothesis, and we hired 100 of the best number theorists to work full time on this, I don't think we would move the needle that much on this, and it would not be a good use of resources. It's a problem in which we don't even know how to do it in theory, and most of mathematics is like that. Well, at least most of the really difficult unsolved problems in mathematics. I mean, there's certainly at lower levels, there are things that we know how to do, and it's just a matter of getting someone to sit down and actually compute everything. These are great graduate student problems, actually, to get started. But to make the big breakthroughs, often we don't have even to know what to do in theory. So nevertheless, of course, this is the conventional wisdom. So back in 2009, Timothy Gowers asked on his blog whether this could change, whether we could actually do actual mathematical research online in a massively collaborative way, crowdsourcing it. And so he just posed on his blog just as a question. He wasn't. He was basically musing as to whether. So instead of having 1 or 2 people working in isolation, have many people work. And the idea, so in traditional research, you work alone or in a pair, or maybe 3 people, and you don't share what you've done until you've almost finished, until you've polished up your preprints, you get rid of all the mistakes you can find, and so forth, because you don't want to embarrass yourself. And the paradigm that Tim was proposing was quite different, where you'd have lots and lots of people, each working, at any given time, they'd each work for maybe 5, 10 minutes, half an hour, on one aspect of the problem. And then if they had an idea, they would say, okay, this might work, I'm tossing it out there, maybe it's rubbish, and then hopefully someone else will step in and say, yeah, I think that's rubbish. Or I think, oh yeah, that might work. Maybe if you change it this way. So to actually share sort of the raw mathematical thought rather than the sort of polished type of thinking that you see in sort of traditional research projects. All right, so yeah, basically like a big online brainstorming session, if you wish. Right, so yeah, one of his quotes is that if a large group of mathematicians could connect their brains efficiently, they could perhaps solve problems very efficiently as well. Okay, so there was a really positive reaction to his blog post, and said, we should do this. Why don't we actually find a good problem and get it started? So I think within 2 or 3 weeks, I think he wasn't planning to actually start one of these things. He was just musing, but he got so much positive feedback that he said, okay, I will try to organize one. And after some discussion, they he settled upon a first problem as a test case, an approach to what's called the density Hales-Jewett problem. Okay, so this theorem, so I decided to not put too much mathematics into this particular talk. So I didn't actually give a formal statement of what the density Hales-Jewett theorem is. But one way to phrase it involves sort of higher dimensional tic-tac-toe games. Okay, so here is a three-dimensional 4x4x4 tic-tac-toe game, noughts and crosses, and you win if you get a straight line in any one of the directions possible, diagonal, hyperdiagonal, whatever. And roughly speaking, what the density Hales-Jewett theorem says is that if you're playing a tic-tac-toe game and the dimension of the game is high enough, so this is a three-dimensional game, imagine like a 3 million dimensional game, 4x4x4x4, right? And you're playing, eventually one of the two players has to win. See, this is not true for standard tic-tac-toe. Tic-tac-toe 3x3, you can end in a draw. But it turns out in high enough dimension, you cannot end in a draw. That someone will have to win first. And in fact, even long before you fill up most of the board, if your dimension is high enough, even after filling up, say, 1% of the board, already someone has to win. And so no matter how you play. And so this is, roughly speaking, this is the density Hales-Jewett theorem. As phrased, that just sounds like some sort of random combinatorial fact, but it turns out to be a very deep theorem, and it implies a lot of other theorems in combinatorics. So just to give one example, Brian mentioned the work I did with Ben Green, proving that the primes contain arbitrarily long arithmetic progressions. That's essentially a corollary of this theorem, plus some other stuff. Okay, but yeah, so that it is a very deep theorem, and it's one of the deepest results in an area called Ramsey theory. And until Tim Gowers started this project, there was only one proof of this theorem, and it was very complicated. It involved an argument of Furstenberg and Katz-Nelson, which transferred the problem from combinatorics to ergodic theory, but a very exotic, non-standard form of ergodic theory. And even that theorem was difficult to prove. And so there was a difficult paper which very few people had actually read in completion to prove this theorem. And that proof gave no bounds whatsoever. So I said that if your dimension is high enough, then certain things happen. It gave no bound as to when that happened, and so forth. So it was not a very satisfactory proof. I mean, it was a great paper, but it was a good candidate for trying to improve it. So the project, so the idea, I think if I go back a bit, initially Tim was very cautious. So in fact, he specifically said, so I have a pen here, that it is not the case that the aim of this project is to find, a combinatorial proof of the density Hales-Jewett theorem. He was initially much more unambitious. So this was a theorem which is a combinatorial theorem, but it only had this difficult ergodic theory proof, and so it was natural to look for a combinatorial proof, and many people had, and no one found one. And so, but initially he had just the modest aim of trying to work out why all the standard approaches to proving this thing combinatorially did not work and get some better understanding of it. But the project really took off. It started off slowly. Maybe the first day there's maybe 10 comments on his first blog post. But people got interested. I started working on it. Many other people started working on it. And we tried all kinds of things. We eventually found some model problems to work on, and we solved the model problem. We got very excited, and after about a month of really intense activity, I think there were like a dozen blog posts, and in each one there was like 100 or 200 comments by maybe 24 mathematicians. Across the spectrum. So Tim and I, but some ergodic theorists, some combinatorialists, and some amateur number theorists amateur mathematicians who contributed some, for example, some valuable computer experiments. And we actually found a combinatorial proof. And we actually wrote it up, and Tim actually sent it to the Annals of Mathematics. We decided to not to actually have 3,000 authors or whatever like we do in physics or life sciences, but we made a pseudonym, DHA Polymath, DHA for density Hales-Jewett. And it got published in the annals as and we found a simple new proof. Since then, actually, one of the participants, my former student Tim Austin, found another ergodic theory proof, which is also much simpler than the first Mercastor-Nelson proof. But this was 40 pages and very self-contained, and it gave a good bound and everything. In fact, actually, in many ways, if you want the shortest self-contained proof of my theorem, Ben, on primes in arithmetic progression, you would use actually this is part of the argument. Okay, so that was the first polymath. That was quite successful, and so of course it was natural to keep going. So we started the Polymath Project, I guess. It was, I mean, that's the official thing that we called it. But it's not. But it was not sort of a really high budget thing. In fact, we have a zero budget. I think. It was all run with sort of off-the-shelf, free software blogs and wikis and so forth. But we ran a few more of these projects. We tried a few things. Most of them. So there's been 9 Polymath projects so far, plus some things that are like Polymath, which things that we didn't officially call Polymath, but they were sort of like Polymath. We had these things called mini Polymath projects, where we would take something like an Olympiad problem, something which is sort of known to have a solution, and we would just try to get a whole bunch of people to crowdsource a solution. The actual Olympiad problem is that you have 3 hours to solve 3 problems, and we have one problem. It turns out that actually with the crowdsourcing, we're actually slower than a good Olympiad student. It takes like 24 hours for a solution to emerge. But still, these were fun experiments. We had a bunch of projects. Unfortunately, most of them actually turned out not to be as successful as the first one. I mean, they usually start the same way. There's a big burst of activity at the beginning where lots of people are very enthusiastic. They propose all kinds of things. And then slowly, like different avenues get eliminated. Some people drop out when they realize that their favorite method is not actually going to be successful. And unfortunately, sometimes we eliminate everything. And sort of all the approaches we try, we hit a brick wall, and then people get frustrated, and so it peters out. So some have, and then sometimes we get partial results, but we can't get anywhere near to our original goal. So I think of the 9, maybe only 3 or 4 have really been you could categorize as successes. I mean, we're still trying to work out what works and what doesn't. But the most recent successful one, and the one that I was really heavily involved in, was last year, was Polymath 8. And so this was the project on bounding gaps between primes. So as I said, Yitang Zhang last year, in I think March of last year, had this great advance on the twin prime conjecture. So the twin prime conjecture says that there are infinitely many pairs of primes which differ by exactly 2. And we can't prove that. And until recently, we couldn't even prove there were infinitely many pairs of primes whose difference was bounded. But Yitang was the first to do that with this really nice argument, recombining a lot of previous arguments in a very ingenious way. He got the infinitely many pairs of primes who differed by 70 million. It's the first finite bound that he got. Now, when he was writing it, he knew that this was not the best possible. This is just what he wanted to write a nice, clean paper. And so this was the bound that came out. And then he said this result is not optimal. There's another number, 3.5 million, that is involved. It's also crude, and there's certain ways to relax it. And to replace this bound by a value as small as possible is an open problem that will not be discussed in this paper. So as far as he was concerned, he was done. But this proved to be quite irresistible to all kinds of mathematicians. When you have a really high-profile result like this, and you say, no, this can be improved, but I won't do it. Then it's so pretty quickly, and because we're in the modern era, it's just on the internet. People basically all over the mathematical internet, and there's now many sites discussing research-level mathematics, started chipping things away. So I think a week afterwards, a friend of mine, Mark Lugo, he said, well, this one equation, the first equation here, if he optimizes into, for 5 minutes work, he can change this 70 million to 63 million. He jokes that so I mentioned this in some blog post or something. He said that, I've always wanted you to mention some of my work on your blog. Just maybe not that one. He's done more substantial work in mathematics, but yeah. And then Tim Trujian from ANU, he made another observation that reaches 60 million, and then Scott Morrison, who I think works in topological quantum field theory, did another tweak. He just had he's good at programming, and he got 59 million. And then I started getting interested, and I said, okay, I can actually squeeze it out of 58. And then on Scott's blog, actually, people started contributing all kinds of improvements. So so Scott soon afterwards said I can do 57. And at some point, then we started optimizing other parts of Zhang's paper and said, hey, now I can get, hooray, we built 50 million now, 42 million the next day. Okay, soon we're like in the 13 millions, and 300,000 and so forth. Okay, so that was 4.9 million and so forth. So spontaneously, people just started. Because this is in contrast to sort of regular mathematics where you have to work for 3 months, 6 months, a year before you can have something you can publish. This type of thing you can work for 10 minutes, okay, and then you can get the world record for this problem very briefly before someone else steps in. It became very addictive actually. I wanted, in fact, I was working on a much more longer-term project, which actually I've still not gotten back to. But it was so much easier to make progress on this problem than the other thing I was working on. So at this point, it was sort of clear that we should do this more systematically. What you didn't want to see happen was like some huge scramble where maybe on the archive, different people were posting every day, saying I can get 3.4 million, and so there would be a huge mess. So I actually proposed that we make a formal Polymath project because we'd done things like this before. And so we proposed a project to, most ostensibly to improve the bound, which we were already doing, but also to actually understand what was going on, to actually figure out how Zhang's argument works, simplify it, and how to connect it to the rest of the literature, and just to digest it, basically. And so this, and since it's already going, people basically immediately said, yes, let's do a Polymath project. So this ran for about a year, and it was really quite intense. Pretty much, for me at least, it took up pretty much most of my research time for the last 12 months. It was, the progress just kept, at times it was just improving day by day. So, for example, this is the wiki page where it shows the timeline of improvements. The most, and H is the bound of gap regime primes. So it starts off at 70 million, and it just kept going down. It's day by day, often it would just drop because of various improvements in various parts of the argument. One nice thing about Zhang's argument, which was well suited for this Polymath style project, was that the argument split into like 4 or 5 pretty much independent pieces. And the final bound was basically, you just optimized various parameters connecting these pieces together. And so we split into groups where each group worked on one part of the project and sort of optimized that bound. And as soon as they got an improvement, the next group sort of jumped on that and plugged it into their machine. And we got this very nice assembly line. You make an advance somewhere and it just propagates. 5 hours later, you now have a new world record and so forth. It was great. So this lasted about a year. It was quite a complicated story. I have to take a whole hour to explain all that happened here. So there's some other mathematicians outside the project also made progress, and then they joined the project, and lots of things happened. Eventually, we got down to a bound of 246, and we published that, and that's where it stands. We could maybe, with a lot of computer power, maybe shave a few more, maybe 240 or something. But we were encountering significant difficulties getting below that. And we know that none of what we can do can ever get below 6. We now have a very concrete obstruction that blocks us getting below 6. But we got down to 246. And so that was that. So it worked really well for us. So some of the things that worked well for us for this particular project that we didn't always have in other projects. So firstly, there was an intense interest in this problem. So many of you may have already heard about some of the story. Certainly, in our experience, whenever one of us went to a university to give a talk or something, there was always somebody who would come up and say, "What's the world record? Where are you at now?" Okay. People were following it. I mean, it's it was like a sporting score or something. As I said before, it was very modular. We could split it into smaller problems, and you didn't need expertise. So there was a lot of difficult mathematics in Zhang's work. Like, for example, he used Deligne's work on the Riemann hypothesis for varieties, which very few people actually know in full detail. But that's only part of that only involved part of the argument. And there were other people, not even in number theory, who could contribute. One nice thing about this particular project was that we had a very easy metric to measure progress, which is this bound. And it was pointed out to me by Ben Green that this is a bound which was guaranteed to terminate because it was a decreasing natural number. So by the world ordering principle, you always stop. And the thing is, the community, the participants was really positive. People were very generous with the time and effort, and they were willing to make mistakes in public and just share, things that didn't quite work and so forth. And it takes a bit of getting used to participating like this, but when everyone else is doing it too, it was a very open and frank discussion, and this was very important. And we didn't use fancy software, really. I mean, we basically used technology that was just available off the shelf. It could be that if we custom design, you spent a couple $1 million or something to get some really fancy software, maybe we could do things slightly more efficiently than we did. But at this point, it doesn't really make, that's not the bottleneck. The real bottleneck actually is getting people to run the thing, actually. I mean, it was really, there was really certain serious advantages to operating in this fashion. Like, if you needed a computational task, someone would do it for you, and someone would set it up, and within hours, you could just muse, I wish, someone could compute this, and someone would actually do it. At some point, we needed a web page set up to collect all these things called admissible tuples. And one of us used Program for a few days and actually set up this really nice web page these are things which, if you're just working by yourself or with two other people, you probably wouldn't have the expertise to do things like this. But any sort of speed bump that we encountered, if there was a paper that looked relevant but we didn't have access to it, within 20 minutes, someone would say, here's a link, to this. And, we also got lots of great contributions from people who were not in the area, but they were following. I mean, they just wanted to follow. So, we had a really important contribution from someone who was not a number theorist. He worked in numerical analysis, but at some point we needed to solve a variational problem, and that was his area of expertise. And so he contributed this. He said you shouldn't be doing this variational problem this way. You should do it this way. You should use what's called the Krylov subspace method, and that was a much more efficient method. And so we just kept getting all these contributions like this, which if you were doing things traditionally, you'd probably never even think to ask the numerical analyst, for example. So it worked well, but sometimes these things don't work so well. I think they do work well if you have, you need to work in a project which is fairly accessible to a really broad area of the mathematical community. If it's a very specialized area and only 20 people in the world really know enough of that area to actually make contributions, then it's pointless to have a Polymath project. So far, most of the projects that have worked well have been in areas like combinatorics, number theory, or analytic number theory at least, and computer science, where at least the questions are fairly accessible, and for which you can split the problems up into toy problems, things that you can work on in a very modular way. One problem we still have is that we don't have a good way of recognizing contribution. So as I said, we agreed to write these papers under pseudonyms because we couldn't figure out how to assign authorship. Like if someone makes one comment out of 1,000 and it's somewhat frivolous, but is this person a contributor or not? And on the wiki page, we have lists of who it's a self-sign-up sheet that if you feel like you're a co-author, you put your name on this web page, and we just rely on the honor system to keep everyone honest. But for formal publications, we use a pseudonym. which has caused some problems. In fact, I put one of these Polymath papers on my CV, and then the administration sent it back saying, you can't do this because you're not the author of this paper. So yeah, you have to put it under other activities rather than actual formal publications. So this is potentially a problem, especially for junior people for which these sort of citations and so forth are really important. But you got a lot of informal recognition. You didn't get a lot of formal recognition. So a lot of the participants of this particular project, they reported that everywhere they went, someone recognized them as someone who was participating because they can follow the blogs, they can see all the comments. So you get a lot of informal acknowledgement of work here, but not sort of traditional formal recognition, unfortunately. Yeah, and yeah, as I said, one of the big things is that you really need someone to moderate. In the beginning, we were sort of naive, and we thought that these projects were so spontaneously self-organize into the right direction. But if, this doesn't happen. You need someone to keep guiding the discussion. Every so often, you make a new blog post summarizing what happened before and trying to keep pushing the direction in the right way. This is very, very time-consuming. And we don't have many people who are willing to do that. And so I don't think there's going to be that many projects. We'll still maybe churn out one every year or two, but it's not a high-volume thing. Currently, we don't. These projects, all the ones that have worked in cases where we sort of knew to some extent what to try. That there were some things we could do. That it didn't require a complete breakthrough out of nowhere. I don't think we know how to crowdsource anything like that. But in an area where there's lots of things to try, and what you need is manpower to everyone to try one by one all the different things, and to see what works, what doesn't, and to sort of collate all the information together. This is the type of thing where Polymath would work very well. Yeah, so it's still nowhere near the scope. So this is nothing like the Higgs or the Genome Project, but. I do think we'll see more, maybe not Polymath per se, but I think this is part of the future, that we're going to see a lot more collaborative projects, maybe more systematically organized than the sort of ad hoc things that we're doing. But yeah, I think one day we're going to have big math the same way we have big science, I think. Anyway, thank you very much.
So we have 5 minutes for questions. Does anybody have any? Jacob?
So the publications of PHJ Polymath,
Yes.
how do those get written?
Right, so...
Can you repeat what the question was?
So the question is, how do these Polymath papers get written? Yeah, so I said it took 12 months to do this Polymath project. I think the actual research time for Polymath 8 was maybe 2 or 3 months, and by far the longest period of time was the writing. And so what often happens is that somebody has to volunteer to do a large share of the work, to start the skeleton going, and to start farming out sections for people to write. We used things like Dropbox and Subversion, and it actually worked out pretty well. We had a lot of very energetic people who wanted to see the whole thing to conclusion. And one thing that was very good, you get a lot of proofreaders. So you have maybe 4 or 5 people doing the bulk of the writing, but a lot of people were checking different sections line by line. So, but that takes a long time to finish it before everyone signs off on it. But it does. We're quite proud of with the writing at the end.
Any other questions? Yeah, Mary.
Hi.
It helps in doing interdisciplinary research, like problems in biology or physics, say, but it's hard for mathematicians to understand what the math problem is. And if different people come and try to explain it, maybe getting a lot of information from different people could help mathematicians find out what the math problem is, or if there is any problem to think about.
Right, yeah, so the question is whether you could use this format for really interdisciplinary activities. That's a great question. Tim Gowers once proposed, actually, I think the origin of life as a possible math project. This didn't go over so well. I think you do need a common base. So we have had projects which, like the Polymath 8, it spanned different areas of mathematics. There was number theory, there was numerical analysis, There was some combinatorics. But everyone participating, we all came from a mathematical background, and so we had this sort of common language that we can speak. I think if you wanted a really collaborative interdisciplinary project, there may be more of a culture barrier. I think it's worth trying. You need the right problem, though. Yeah.
Any other? Michael?
Not exactly in the same direction, but sorry. The laureates have donated $500,000 to a fund that will allow students to continue to study in their home countries rather than study in the main universities. It occurs to me that if this is with respect to the brain drain, this is only one of the problems. After they finish studying, if they want to continue to do research, they find themselves isolated, the only people in their countries who actually are familiar with the material. This seems to be not necessarily as solving unsolved problems or improving on problems is not the only possible application of this kind of collaboration. It would also be a way to allow people to remain in their home countries and yet be part of an international collaboration.
I'm not quite sure what the question is, but yeah, so some of the feedback I certainly got from these projects that was that for many students, particularly those not working in top-tier universities, this was one of the few places where they could see mathematical research behind the curtain, to actually not just see the finished products in published journals, but the sort of how the sausage is made. That you try lots of dead ends and you don't know the dead ends until you try them, and you keep eliminating certain things and making progress elsewhere. And even really top people make a lot of mistakes initially before they find sort of the right approach. So a lot of graduate students, I got a lot of feedback from undergraduates and graduates saying this is very revealing. So I could imagine, particularly for students in the developing world, maybe, or for people not sort of in the center activity of elite universities, there could be some value in having these open sort of mathematical projects beyond just of the research aspect.
And participation.
Yes, although again, there's this issue of assigning credit and so forth, which we haven't solved. Yeah, maybe if there's some formal way to accredit participation, there could be some way to have some concrete encouragement for participation. But I mean, with these projects, it was so important though that we don't just sort of say, round up 100 random people and say, okay, you all go to work on this project. I mean, it's important that people volunteer themselves, and it's sometimes not obvious that the expertise is needed until the project reaches a certain point, and then then they find out that what's needed, that what they do is exactly what's needed. So, I mean, it's not like you could sort of sign up for one of these things and expect that you could contribute unless you already knew that there was a good fit between your expertise and one of these problems.
One more question? Are there any more? Okay, let's continue.